Thank you everyone for attending STP04, Aetion's migration journey to AWS CodePipeline, CloudFormation, and ECS. I'm the systems engineering manager for a company based out of New York City. We focus on healthcare analytics. We also have offices in LA and Boston. And without further ado, let's talk about the agenda of what we will cover for today. Number one, I'll briefly talk about what Aetion does, what the Aetion Evidence Platform entails. Then we'll speak to what the makeup of the systems engineering team. And we'll dive immediately into the technicalities of our platform. What are the primary components? We will then move on to speaking about the legacy build and deploy architecture, the problems we face with that, and how that influenced the problems in the overall architecture. Then finally moving on to how we devise a solution to solve those issues, the migration itself. And we'll also allude to what we are working on for the foreseeable future in the coming months. So what is the Aetion Evidence Platform, and what does Aetion do? We are essentially a healthcare analytics company that leverages the medical science of epidemiology, where we attempt to provide real-world evidence-based outcomes. And in other words, what that means is we work with institutions who will provide us with their large data sets. We will upload it onto our platforms, and then we'll have their scientists execute analyses on specific populations. And the result of those analyses will influence research studies in the biopharma and healthcare space in general. I'm in no means qualified to speak about the science itself. I'd be happy to put you in touch with folks who can answer specific questions. So do see me after that if you would like more information on what we do in terms of the science itself. One point to mention before moving on here is that we are a platform offering. So we have two types of offerings. Number one, we have the primary cloud offering. We also do have an on-prem offering. However, we are primarily going to be focused on speaking about the ECS migration and the CloudFormation components for the cloud offering. The on-prem offering is a secondary offering that we have. So before moving on, just want to give a brief shout out to the makeup of the systems team. We have an engineering organization which is about 30 or more engineers, and overall we are a company of more than 100, Series B, continuously growing. The systems engineering team specifically is about 6 people, including myself. We've got Scott in LA, we have Abe, Dinesh, Peng, and Steven, based out of New York. Peng is actually with us today. Unfortunately, the rest of the members couldn't make it here. Obviously, they're more happy keeping the lights on than being in Vegas. So these are their 10 seconds of fame. And with those 10 seconds being up, let's talk about the primary components and what the overall tech stack looks like at Aetion. So we've divided this diagram into two components, client services and central services. And the reason we're making this distinction is client services actually represents a VPC on a per client basis. So yes, we deploy all the services that you see inside the client services box to every single client. So if we have 25 clients, replicate that box by 25 times. Obviously, that is a scalability problem, but initially when you're bootstrapping a company, this was done because it was easy to solve the security problem. We won't be covering the issues with running multiple VPCs on a per client basis throughout this presentation, but I will speak to the problems of this and what we're looking to solve this in the what's next phase at the very end of the presentation. The central services is another VPC. These are the services that are shared across all of our client services. And the way we share these services across client services is we have VPC peering between the client VPCs and the central VPC. The central services, as you can see, contain things like the authorization service, the administration service. If we need to generate a plot based off of an analysis, the backend will reach out to the plot service that is going to piggyback off of a VPC peer connection sitting in the central services VPC. Another point to note over here is that primarily you'll notice we are a Java-based shop and a MySQL-based shop, barring the report services, which are fairly new, and our front end, which is Angular. Report services being React-based, and they're React-based because it's something that we developed recently, and Angular being our front end. Everything else is Java and MySQL-based. And we have a set of job dispatchers that are actually separate from our primary backend. This is where each one of our jobs are regulated and executed. Inside the central services component, there are two things to note over here. Number one is Chef. We are, from a legacy standpoint, a heavy Chef-based shop, and you'll hear Chef quite a few times today because it does directly impact the issues we face in moving to, and why we moved to a new type of code pipeline, CloudFormation, and ECS-based architecture. We also have Fabricator here, and one item that might not be here is Jenkins. So we use Jenkins as our legacy build tool. Fabricator, if you haven't heard, is an open source tool by Facebook. It's essentially another version of Bitbucket, which is self-hosted or cloud-hosted. We have always been using Fabricator, and we'll talk about how we'll potentially move off of Fabricator as well. We are moving towards GitHub. But these are the primary components that make up our entire application stack. And with these being covered, let's talk about how they're being used, and we'll start off with the legacy build architecture, or what does the build flow look like. So we have 3 phases over here. Number 1, we have the commit phase, where a developer will go ahead and make a commit, and that code will end up in the Fabricator repository. The only reason it says arcdiff master over here, that's equivalent to a pull request in GitHub, but if you're using Arc coupled with Fabricator, that is the kind of command you will issue. So a developer would be ready to commit code, he would arcdiff master it, it would go through a local lint, it would go through the review process, and if that's successful, it will be pushed into the Fabricator repository. Fabricator is a self-hosted version again, which is running on an EC2 instance. It is clustered for high availability. Then we move on to the build phase. The build phase has a Jenkins box, and this Jenkins box is basically polling the Fabricator repository for any changes. Again, Fabricator simply hosts Git repository, so there's nothing really unique over here. And when that polling happens, it finds a change. It will then go ahead and attempt any kind of build based off of the requirements of that Jenkins job. So in this case, let's say there would be a Maven build that will happen, and the output of that Maven build after the integration test and the unit tests have been completed would be a Docker container. And we would push this Docker container to a self-hosted Docker registry based off of EC2 as well. So a few issues over here. Number 1, Jenkins is a standalone box in this architecture. So if it goes down, we're done. Number 2, the Docker registry is also a standalone box over here. If that goes down, that's also obviously a problem. And so there's no sense of high availability or fault tolerance. We relied purely on EBS backups and midnight snapshots. But despite that being an issue, this works just fine if you're bootstrapping a company and you simply need to create a build environment and you're pushing out Docker images. However, this does start to unravel when we speak to how we're going to actually deploy. So the next phase is the legacy deploy architecture. How did we ship the code? Over here, we have 3 phases again. Number 1, we have the commit phase, then we have a Chef update phase, and then finally the push phase. So this is where things get interesting. Why do we have a commit phase for our deploys? Well, Chef is actually very prominent across our legacy infrastructure in the sense that Chef is the one that provisioned those EC2 instances and all the resources across the board. Chef configured those EC2 instances, and we made the cardinal mistake of also using Chef for deploying our application onto those very own instances. So what does that process look like? I've got a Chef global file which has every single client VPC. I want to deploy, let's say, a new version of the front-end container to the front-end EC2 instance. I would go to my Chef global file. I would update the Docker, I would update the Docker tag number that I've obtained from the build phase. And once that update has been made, it goes through a normal Fabricator repository process. It's pushed up into the Fabricator registry. Jenkins is now going to poll that registry. It sees that there has been a change, and now the Jenkins job is responsible for executing a job whose responsibility it is to actually update the Chef organization. Because the Chef organization is where the information is stored on what Docker container I need to deploy on that particular instance. So once the Chef organization has been updated, now I can do one of 2 things. I can either manually SSH into any one of my backend, front-end, or worker instance boxes and run sudo chef client so it can pull the latest changes down, or I would wait for the next Chef interval. In dev, this happened to be 5 minutes. In production, it was 15 minutes. Obviously, this is a huge problem because we managed to create a pull-based architecture and not a push-based architecture when it came to application deployments. And not only was Chef deploying a new container, but it was also downloading configuration. So there were a variety of things that were being done, But this is a brief snippet of what the primary components of Chef's responsibility was here. Number one, update the configuration files. Number two, download shards. What I mean by download shards over here is, in our legacy architecture, we actually had to download those data sets onto those local EC2 instances. And that was also a part of a deployment process. So we actually had two types of deployments. One, the standard version deployment for an application code update, and number two, a data deployment specific to a client or a customer. And this was also handled by Chef. And then number 3 and 4, it would stop the existing Docker containers, pull down the latest images based on what was provided in the Chef global files, and then it would be responsible for deploying the new Docker containers as well. And we had some kind of hacked custom logic that if anything failed there, hopefully it would roll back to the previous container. Obviously, that didn't always work out. So again, I also want to be clear over here that we're not hating on Chef in any way. Chef is a fantastic tool when you use it for configuration in the right manner, and also if you leverage provisioning in the right manner. But when you start using it for deployments, it's really outside of the scope of what the tool can do. Obviously, you can hack together any type of scripts, but when you go to a point of scalability and you're suddenly adding more clients as a Series A and Series B company does, it becomes unmanageable. So this was the type of architecture that we inherited that was problematic. So with those problems, let's talk about what this looked like for the overall legacy architecture. So to your left, you would start off with the user hitting the browser, and you would go to xyz.aetion.com or client.aetion.com. DNS magic takes place. It goes on to Route 53, and Route 53 will now forward your request down to an elastic load balancer. That elastic load balancer now forwards that request to an Angular instance, to an Angular container, which is our front end. And Angular would then forward that request to our backend, which is Java-based. And if the user was attempting to log in, the Java backend now needs to communicate with the authorization service sitting in the central services VPC, and it would go ahead and make that connection over the VPC pure route. If the user had suggested that, if the user had performed an action which would require the execution of a job, that would queue up something in the database, and then we would have our worker dispatchers who would be constantly polling the database and execute the job on demand. This is actually depicting a static dispatcher where it was always sitting there idle, but we have converted those into dynamic dispatchers. That is outside the scope of this presentation. We actually did present our movement towards dynamic dispatchers last year at ECS, so if you would like more information on how we did that, we'd be happy to provide it. But with that being said, what you see over here with the back-end, front-end EC2 is not actually a mistake. The front end, the back end, and the MySQL database did live on a single EC2 instance. I don't know how we managed to do that, but I can tell you when we inherited this architecture, there were many sleepless nights as a result of that. So number one, there's no fault tolerance, there's no high availability. The RDS, if it goes down, if MySQL goes down, then we're toasted. We simply rely on those EBS snapshots that happen on a nightly basis. Furthermore, every single one of these items, as mentioned earlier, is managed by Chef. So these boxes were provisioned through Chef, and we had the same kind of deployment pattern, not just for our back-end or front-end instances, but also every single one of the central services you see. And those central services, although in this diagram we don't indicate where the databases live, those databases were also co-located with their Docker containers. So it was one single type of deployment pattern, one single type of architecture, where if a single node went down, that's it. That was the end of being able to log into the platform or performing some kind of analyses. And given we were a monolith, we weren't necessarily able to handle these failures as well. The only exception to all of this that you see over here are the report services. And the report services were essentially our POC onto ECS, CodePipeline, and CloudFormation. So reports and reports UI, reports is a Java backend, reports UI is a React front end, and both of these items run on ECS and are deployed through the CodePipeline via CloudFormation, which we'll speak to later on. And they also leverage AWS RDS. So with the overall legacy architecture being displayed there, just to summarize once more, what were the problems that we had? Number one, the build phase is disjointed from the deploy phase. Number two, the deploy model is pull-based via Chef. It's not push-based. You rely on individual actions to take place on in a manual scenario to actually update your applications. Chef does everything, and obviously that's the highlight of the biggest problem that we had. It provisions, it configures, it even does deployments. In fact, we had JVM parameters that were somehow being passed through Chef as well for some of these applications. So we did quite a bit. It was pretty impressive from that perspective, but not in terms of reliability or stability at all. Of course, no database and app level high availability, and because we're a fairly monolith application, auto-scaling was non-existent, and we had to vertically scale, and there was no sense of horizontal scalability. Monitoring was limited. We're not really going to refer to that in this presentation, but that was part of a bigger problem that we had. CICD non-existent, we've already spoken about that. And decentralized logging, because everything was a container running on an EC2 instance on its own, those logs were local to that particular instance. And of course, Chef would put out a log rotate script, which would ensure that the disks don't fill up, which didn't always work. But with those problems in mind, there is hope, or rather there was hope for us. And what did our solution roadmap look like? We basically broke it down into a set of short-term initiatives and long-term initiatives, and it spanned from a few weeks to more than a year. And this is not an exhaustive list by any means, but these are the primary components that we'll essentially cover today. Number one, we recognize that, hey, we are a software company, right? Our bread and butter at the end of the day is being able to ship software. We need to be able to do that on demand, and we can't have systems spend 50% of their time on deployments. It doesn't have any benefit to the company. So we decided that CICD is one of our utmost priorities. Why is it that I'm referring to semi-CD over here? That was really just internal language we use for our own stakeholders. And what I mean by that is, depending on how you define CD, it can refer to continuous delivery or continuous deployment. And again, depending on how you define those two, continuous delivery generally is generally classified as the ability to push a container or an application across a pipeline, whereas continuous deployment is I push code and I commit code, and it's going to end up in production as soon as possible because you've assumed that everything, including the testing piece, has been automated. We recognize that for us to be able to do continuous deployment, it was not going to happen overnight. We would have to change the entire developer workflow. We would need more scrutiny when it came to testing, and we would need a better level of automated testing. So we simply are referring to continuous integration, and we're referring to this as continuous integration / semi-continuous deployment. Number two, dynamic dispatchers. Again, this is not part of this presentation, but one of the reasons that we looked at dynamic dispatchers was we recognized that our dynamic dispatchers were actually, our static dispatchers were actually sitting there idle most of the time, incurring additional expenses. And if we leveraged ECS and created these workers on demand, it would not be an issue for us and we would save a ton of money. This was actually our first foray into ECS, which sort of translates into number three, which is the rationale behind migrating all of our applications to ECS. Number one, we would obtain a sense of high availability because of how ECS is architected. Obviously, there is an onus on us to ensure our applications are stateless, but it would enforce us to do that naturally as part of this migration. And rolling deploys are default as part of ECS. So unless we're looking at blue-green or red-green types of deployments or red-blue based deployments, rolling deployments work just fine for us, and ECS provided that out of the box. Reducing a maintenance headache, obviously you no longer have to maintain Docker containers across EC2 instances that have their own management capabilities and their own management headache that comes along with it. A common question that arrives over here is why use ECS, why not Kubernetes? When we were having this discussion, it was about a year ago, we looked at a variety of factors. Number one, we were a small Series A organization. The amount of time we would have to allocate to resources for working on Kubernetes was not something that we could do at that point in time, but we had already POC'd dynamic dispatchers on ECS. It worked wonderfully for us, and we decided to therefore move down that route. That doesn't mean we completely eliminate Kubernetes. In fact, I'll refer to that at the very end of the presentation as well. But ECS was our go-to, and we decided to move forward with ECS itself. Number four, migrate all databases to RDS. This is pretty straightforward. We didn't want to deal with our own clustering, with our own slave-master relationships, and RDS does the job really well. So we decided to move on to RDS. In fact, as part of this migration, the first thing we did before we modified anything was move those MySQL instances onto their own RDS databases, because that allowed us to really play around with the rest of the infrastructure in more easier fashion without impacting the client or the customers. Number 5, reduce the chef dependency. And this really comes more from, this doesn't come from a tooling standpoint, this comes more from a design and architectural standpoint. We didn't want to choose a new tool because it was cool. Terraform is all the buzz these days and everybody wants to use it. That doesn't mean Chef can't do its job. It has its abilities and it has its own area where it does the job really well. But based on the problems that we face, we wanted to ensure that our provisioning, configuration, and application layers were absolutely independent from one another and that they would not interfere with one another. And in order to enable that, we decided to introduce 2 new tools, which were Terraform and CloudFormation. And why Terraform and CloudFormation? Because technically they can do the they can produce the same set of tasks and the same set of results. I'll get into that later on in the presentation. And number 7 is for application and infrastructure level monitoring. We explored a bunch of tools, but we settled on Datadog. It seemed to work for us well. New Relic was another option that we explored. There was no particular reason why we chose one over the other. We thought that both were compatible, and I think it just came down to pricing for choosing Datadog. So that was the solution roadmap. And now, what was the first task as part of this journey that we embarked upon? It was the big fish, which was let's enable continuous integration and semi-continuous deployment. And why do CI semi-CD? Some of these have already been mentioned. Number 1, reduce the strain on the systems team. We want our engineers to focus on the application layer and the scalability of the infrastructure rather than spending 50% of your time deploying. Number 2, it automatically enforces our move towards a microservices-based architecture, which we were already headed towards. And so if we're enabling CI semi-CD, we have to absolutely ensure that by the time we get to microservices, we have this set in stone. Number 3, it was a smoother transition to us for Elastic Container Service because we had already done some of this work on the ECS side. It enforces a transition to the AWS CodePipeline suite. I'll talk about that in the next slide. But number 5 is simply plagiarized from another Amazon presentation, which is if you implement CI/CD, it improves developer workflow, which results in improving the developer output, which potentially increases the developer happiness. When we asked our developers after the migration, were you more happy? Their reaction, aside from whatever happiness they may have, was, oh great, we now have to learn AWS. So how did we proceed on doing this? Number 1, again, throw out Chef, reduce the dependency on Jenkins because it was treated as a monolith. We wanted to leverage more modular tools. Number 3, migrate to pipelines as code flow. What that means is this notion of why were we using a pipeline, it stems from the fact that we want the preceding action to influence the next action. So if something failed in the CI environment stage, we don't want that being deployed to the QA stage. And it also enabled us to put in manual interactions to ensure that there was a separation of concerns. And finally, leverage the AWS CodePipeline ecosystem. So a common question here is, why did you use the AWS CodePipeline ecosystem, which consists of code commit, code deploy, code build, CloudFormation, and so forth, and not other tools such as GoCD, CircleCI? Those are all fantastic tools. We had engineers within our team that had used those successfully in previous companies. We had a few limitations on what tools we could use. Recall that we used the self-hosted version of Fabricator. So most of those third-party tools did not integrate well with Fabricator. And while AWS CodePipeline doesn't integrate with Fabricator either, we did find a way to temporarily make that integration. But more importantly, we found that AWS CodePipeline actually did not lock us in to a specific set of tools. It did for, say, CloudFormation, of course, but that was intended and intentional on our part. So it provided us that level of modularity that we were seeking. But what does that modularity look like? You can see it in the end result of this entire pipeline. So what does this CI semi-CD pipeline look like today? This is exactly what you're seeing. Again, we have the commit phase. Why do we have a commit phase? Because every single application is treated as a microservice. And so within that application repository, we now add 2 files. Number 1, we have a build spec file. I'll speak to what that build spec file does, but it's related to AWS code build. And number 2, we have a AWS CloudFormation file, and that is leveraged in the deploy phase. So I am a developer. I make a code change. I commit my code. Fabricator has the latest change. How do I get that change to invoke the pipeline? When we were leveraging the AWS CodePipeline at that point in time, the CodePipeline only allowed invoking actions through 3 items: AWS Code Commit, AWS S3, and GitHub. We were neither using GitHub and nor did we want to use the other ones. So we decided to create a temporary mirror hook between the Fabricator registry and AWS Code Commit. While a developer always committed to the Fabricator registry, he or she did not know that in the back we were actually doing another mirror push to a duplicated repository. This is not recommended, but we were able to get by with this simply because of the fact that it was not exposed to the developers and only systems engineers knew how to touch it. And if something did break, you knew who to find. But the primary reason for having AWS Code Commit, again, is only to invoke the pipeline, and this would be replaced over the next few weeks by GitHub, in fact. Once Code Commit knows that a change has been made, it then pushes the change down to AWS Code Build. And AWS Code Build will begin the build process. So how does it know how to begin the build process? It does that by looking at the application repository. Again, that build spec file. That build spec file actually has 3 phases. Those phases are pre-build, build, post-build, and a 4th phase being artifacts. The pre-build phase is where you specify, I want you to install the dependencies I need. I need Maven to do a Maven build. I need to do a Java build. I need Node.js to do a Node.js build. Once those dependencies are implemented inside the AWS Code Build container, it will then proceed on doing the build. If there are any unit tests that have to take place, those tests will also take place. The end result of that is just like in our previous legacy architecture, a Docker container. What's unique about AWS Code Build, and one of the reasons why we wanted to use it is a service by Amazon that only starts up when a commit has been made and a build is now required. So whereas Jenkins was always sitting there as a monolith, we were always we were wasting quite a bit of money. Now that being said, you can do the same thing in Jenkins by leveraging workers. So that was always a possibility, but since we were adopting AWS CodePipeline and AWS services, it was a simple hook for us to be able to use Code Build because we were already creating these images using Maven for the Java-based applications. And as soon as the Code Build container completes the build, it actually goes away. So we only actually pay for the duration when the build takes place. Now, once the Docker container is pushed, previously we would push it to our self-hosted Docker registry, which was not highly available. Now we push it to Amazon Elastic Container Registry. As a result, we don't have to worry about maintaining any kind of server, nor of the high availability for any one of those images that reside there. Once that is complete, we move on to the deployment phase. And while this diagram does depict it as another phase, if you can visualize it as one single pipeline. But the next phase is probably the more important piece and speaks to how we sought to design application provisioning versus infrastructure provisioning. We use CloudFormation to deploy to our continuous integration environment. So why do we use CloudFormation? We recognize that our underlying infrastructure would consist of core components. Those components would be the VPC, the ECS clusters that house those ECS instances, the AWS code pipelines, and the RDS databases. These were components that we didn't want any of the application components to interact with per se, and we wanted to keep them as separate as possible. So we provisioned those independently through Terraform, which we'll get to in another slide. But to go back to CloudFormation was focused on the application components. Naturally, we tend to think that the application is only consisting of a container, but the reality is the application actually has infrastructure components as well, such as the application load balancer, Route 53 entries, security groups, IAM roles, the actual ECS service itself, and the test definitions associated with those ECS services, aka the container definitions that are defined in ECS. So by creating a dynamic CloudFormation template, what we were able to do is at any given time, we can spin up an entire environment for any one of our VPCs as long as we provided 2 things. The ECS cluster where it would be provisioned, and of course, the VPC where we would like to deploy that code to. So on the initial pipeline run, CloudFormation would create the application load balancer, the target groups, and the security groups, and everything else that was associated with it. But on a subsequent run of the pipeline, it would not recreate those resources unless they were modified. And really, the only item that is modified on a subsequent run generally is the task definition because you have a new build that you would like to deploy. So while we solved the deployment problem through CloudFormation, we still lack one issue over here, which is how do we actually start the application within ECS as the container? And previously, we did this by obtaining secrets and the the secrets and the database URLs and the passwords through Chef. We wanted to eliminate Chef, and we started storing these secrets into the AWS parameter store. So in the parameter store, we stored secrets we stored items that were that we wanted to be encrypted, such as the database password, and we also stored non-sensitive items, such as the database URL and the database username. And then at that point, when CloudFormation has successfully deployed the ECS service, CloudFormation will not go ahead and say that this service is up and running until a health check passes. And for that health check to pass, the service has to query the AWS parameter store, obtain the configuration, connect to the database, because if that doesn't happen, the service would not be able to respond to a health check. Once the health check has been responded to, CloudFormation says, okay, this service is up and running, and the code pipeline would indicate, all right, we are ready to move on to the next phase. And the next phase in this diagram is a manual approval, but it can be another deploy to another environment, such as QA. The only reason a manual approval is over here is because of the fact that, again, we wanted to control our releases outside of the CI environment. So only specific people who had privileges, who have privileges to deploy to the next environment had the ability to approve or reject that particular change that would go down that pipe. One item that's not actually mentioned here is with CloudFormation, we leverage change sets. And this is something that was introduced last year that didn't exist for CloudFormation before that. So the manual approval, what it actually indicates to us is what are the changes that CloudFormation is going to make based off of your code commit. So if somebody did make a change to the application load balancer that is not something that is not something desired, you have the option to reject it for that reason. This is extremely important for us in production, especially when we're doing this in our initial phases. So we manually approve. We can now deploy in identical fashion using CloudFormation to QA. And you can visualize this moving on to all other environments. So staging being next, any other environment after that, and the last environment to deploy to, of course, would be the production environment itself. This is a throwback to our legacy deploy architecture, just to highlight the differences. Obviously, we had problems here with multiple tools that were disjointed, stitched together. But our primary problem was the fact that we were unable to successfully deploy something without relying on Chef and the polling-based mechanism. What this allowed us to do is everything was push-based. We knew exactly what was going to happen at any time in the pipeline. And if something did end up in production that was not supposed to be in production, it was either someone approved something that was not supposed to go through, or something was missed as part of the testing phase, which we would need to continuously improve upon. So with that being said, we covered the application pieces, but we didn't cover the separation of the provisioning concerns when it came to everything else, the ECS cluster, the VPC, and so forth. So on your left side, what you see over here is how we are leveraging Terraform to be able to create that underlying infrastructure, being number one, VPC, ECS clusters, pipelines, and RDS. These are the only 4 components that we actually create using Terraform. Everything else, when it comes to the application, is deployed using that CloudFormation and CICD model that you saw before. So that was our separation between using Terraform and CloudFormation. People ask, well, why couldn't you do the same thing in CloudFormation? And that's absolutely true. You could. However, one thing we didn't like at that point in time about CloudFormation was if you modified something outside of the code, which is also true for Terraform to an extent, you were not able to see that drift. CloudFormation did release an update a few weeks ago where there's a drift check, where you can now see if someone modified something outside of the written templates through the console, that, oh, look, someone has modified something, I want you to pull in the latest changes. Terraform already had this capability to an extent. It was dynamic in nature. Of course, it's cloud agnostic as well, but that really wasn't our primary concern because we were pretty satisfied with being on AWS. However, using Terraform also gave us the advantage of, if need be, where we need to be on a multi-cloud provider or in a private data center, we could actually leverage Terraform to create some of those underlying resources. And I briefly alluded to our on-prem model. The on-prem model would also work well for when it came to post-provisioning via Terraform. So what are we using? Again, this is just a recap of everything that's already been mentioned, so I'll quickly move through this. The only item that we haven't spoken about over here is Launch Darkly. To further alleviate some of our concerns when it came to configuration management at the application layer, we decided to use a third-party tool called Launch Darkly. Essentially, all Launch Darkly does is provide feature management, and instead, previously we relied on Chef. So when I said we did configuration through Chef, we didn't just do configuration for the box, but just like for those JVM parameters, we did even more specific configuration, such as, oh, I want to enable this feature. So if you wanted to disable a feature, our monolith was already feature flag based, but it would still require a restart of the application, which was not useful at all. So that was really the only application outside of Jenkins that we leveraged outside of the AWS ecosystem. So what did the overall legacy architecture look like? Apologies that this diagram might be a bit difficult to read, but we went from this overall architecture where everything, as you can see, is co-located onto its own EC2 instance, and the connections that you see are the services going from the client VPC and the central VPC and vice versa to communicate with one another. We do have a layer over here for RDS databases, and we also have a layer at the bottom for ECS clusters. This is actually referring to a later phase of our legacy architecture where we had already moved on to RDS instances, and we had already POC dynamic dispatchers and the report services on ECS. But we went from this gigantic architecture, which only represents 50% of it because it's multiplied by the number of customers we have, to a more simplified architecture, and this is what we currently have. Again, we still maintain multiple VPCs, but if you were to look at it from a single client's perspective, you have two VPCs, a central VPC and a client VPC. And within those VPCs, we have two layers of high-level components. The first layer being the ECS cluster, which houses every single one of those services that you saw, which were previously running on their standalone EC2 boxes. And then number two, you have an RDS layer, which contains all the databases that those services require. And of course, VPC peering is continued, so the services can communicate with one another. And the items that are outside of those particular clusters, and the items that are outside of those particular VPCs are the AWS parameter stores and Launch Darkly. AWS parameter store being used for secrets management, and Launch Darkly being used for feature management. This is obviously a much easier architecture for us to handle today, despite the fact that we still provision multiple VPCs on a per client basis. So at the end of the day, what did we achieve? We definitely reduced costs significantly because when you move to ECS, you start thinking about resources from a horizontal scalability standpoint. So because we couldn't horizontally scale, we now had the infrastructure in place to horizontally scale. So it enforced us to think about our resources as a cluster rather than, oh, this item would require 4 gigs of memory at scale, but you're not always running at scale. This is where I could take that same service, run it at 2 gigs, have an HA component, and have an auto-scaling component, which would simply add another service if that scale were to take place. We achieved CI semi-CD. We've already spoken about that. One of my personal favorites is the removal of reliance on Chef for provisioning and app-level configuration. We separated the two by ensuring that the infrastructure is provisioned through Terraform, and CloudFormation and the pipeline handles the application provisioning component. And as a result of those two items, the new environments that we had to create on a per client basis are now brought up in a matter of minutes versus a matter of days. And the reason it becomes days is because everything was through Chef and everything was correlated, despite the fact that each client being on their own different VPCs, we were afraid to modify our Chef cookbooks because we don't know what kind of divergence has taken place, and Chef would potentially overwrite that. So we would have provisioning jobs that we would be afraid to run if we had a requirement to add a new client. So that's a nightmare because you're saying, oh, I'm a Series B company, I'm growing, and you're telling me I can't add a client, or it's taking me 3 days to onboard somebody. Obviously, that is an operational nightmare, which is no longer the case thanks to the new flows that we've created. Naturally, this simplifies the developer workflow. They don't need to understand Chef. We do encourage them, and we do want them to eventually understand the AWS ecosystem. We do feel that as we go towards microservices, it should be an end-to-end type of ownership, but it will take some time to get there. Regardless, today, they commit code, it ends up in CI, and through the manual approvals, it'll potentially end up all the way into production. We also forced high availability as well as enabled high availability across apps and databases. RDS handled the database piece. Not all of the apps can per se necessarily are highly available in the common sense, but we've enabled it where within a few weeks, most of them should also be highly available. But more importantly, what we did is we altered the focus from an infrastructure component to an application component. So now we can actually focus on the scalability of the app, the security of the app, and the testability of the app. Whereas previously we were worried about the infrastructure just blowing up in our faces, which may or may not have happened a few times. So that covers the entire migration process and what we did to solve the problems we face. But what's out there for us next? And this isn't an exhaustive list again. This doesn't represent what we're doing across all of our multiple engineering teams, but it focuses on the items we mentioned throughout this presentation, or the themes we mentioned throughout this presentation. Number 1 and 2 refer to multi-tenant container architecture and multi-tenant application architecture. I'll talk about multi-tenant application architecture first. For something like this to take place, we would need to decouple our application. So we are taking our monolith and breaking it out into microservices. So it happens for us naturally, and we've enabled CI/CD, so that is not a problem for us when it comes to deployment. But multi-tenant container architecture is what we also look at when it comes to the problem we face with provisioning multiple VPCs. Yes, we've reduced the burden on ourselves to provision those VPCs and maintain those VPCs, but 50 VPCs today, 1,000 customers tomorrow, equal to 1,000 VPCs. You could potentially automate that and make that work, but instead of a graph moving up on the y-axis, moving on the x-axis in terms of maintainability, you'd start moving up on the y-axis because you're taking that same application and replicating it across multiple locations, increasing your footprint on what you need to maintain and what kind of outages you need to look for. So if we could take all of those VPCs, all of those per client VPCs, consolidate them into a single one, that would be far beneficial to us than having to recreate VPCs on a per client basis. That being said, that is heavily dependent on number 3, security and compliance is one of the reasons why we never did this in the beginning. And one of the major initiatives we have for the next year is high trust certification. We are not PHI certified. The only way we are when we do deal with PHI items is because we partner with ClearData. So we actually deploy our entire infrastructure for PHI-related resources into ClearData's AWS environment. That is our temporary stopgap until we achieve our AWS high trust, excuse me, not our AWS, but our high trust certification. They did not pay me enough to say that. High trust certification. So security and compliance are extremely important, and that will potentially modify parts of our existing infrastructure, which is good because it'll make our infrastructure and our application architecture more robust and far more secure. Number 4, exploring Kubernetes to reduce divergence between cloud and on-prem. The on-prem model is actually very simple. It's a VMware image which contains Docker containers. Whenever we're deploying on-prem, we know what kind of version we're going to deploy because it's a closed-off environment. It's a traditional deployment before the cloud era took off. And so providing a VMware image would suffice for us. However, as the business grows on the on-prem side, we would have if we had an increase of VMware image maintenance, that would be divergent from what we were doing in the cloud. And while ECS is only in the cloud, Kubernetes could potentially be deployed to on-prem as well. So that is something that we're looking to explore, but the primary advantage we see from our vantage point at this time around is it would reduce divergence and not necessarily anything else because ECS satisfies most of the other requirements. Also, on-prem models and hybrid models can differ from customer to customer. Some customers will say you can deploy into our environment and we will not provide you any level of connectivity into our environment, whereas others will say, we'll give you a hybrid connectivity. You can connect the 2 VPCs together. You can actually SSH into those boxes, so you could leverage other services to dynamically push code down into their data centers. Also, Kubernetes would be beneficial for us, not just for on-prem resources, on-prem data centers, but also private data centers and ClearData like other private AWS accounts should a customer require us to do so. But this essentially wraps up the majority of the presentation, and we do have quite a few initiatives that are in the pipeline. but these will be the primary ones that we'll focus on for the foreseeable future. I want to give a brief shout out to the team that has worked tirelessly over the last few months to achieve what we've achieved so far. And thank you everyone else for attending. We are hiring, cheap plug for Aetion. Thank you, we'll take questions now.
All right, we are going to be taking some questions from Slido. No? No questions yet. So, how much more sleep do you get at night now that you have infrastructure that's highly available?
You would hope I get a lot more, but I'm still working on that.
Any questions in the audience about going through this journey?
Now that you've got it up, what kind of percentage on your ROI are you seeing out of this endeavor?
Oh yeah. So the biggest ROI percentage that we saw was on dynamic dispatchers by moving them to ECS. And our bill as it was way over the roof. When we spoke to people about our build, they thought we were a unicorn startup. We were only Series B. And we essentially shaved off at least 40 to 45%. And I'm being conservative when I say that on a monthly basis.
So where's your biggest spend now that you've eliminated? I assume compute was the biggest piece by switching with containerization.
Yeah.
So where's the biggest part of your spend now? Is it storage for your infrastructure?
I would say storage is naturally going to increase because of the number of data, because of the sizes of the data sets, but compute will continue to be our primary spend.
Excellent.
Because when we're crunching those data sets, you have to recognize that they require really large instances depending on how big that data set is to be able to successfully crunch those numbers.
Any plans to look into anything on the serverless side?
We did consider Lambda last year, but it was too early for us to look at it. There might be space for Lambda and the serverless components when it comes to our data ingestion pipeline. We are using Lambda for minor things such as notifications down to Slack. So the data ingestion pipeline is probably the primary area. The compute side, the application deployment side, we seem to be pretty satisfied with where we are today.
Any other questions?
What about your cost for the build? Like, how much cost are you incurring on builds? Because you're paying for the code for every time it's building. I know you're getting a reduction, but
for the code build piece.
So every time they keep putting out new code, you're
right.
incurring a charge. How has that affected you?
Oh, you'll love this answer.
Right.
I know this answer.
So it's practically negligible. We don't even consider it. I think we had multiple deployments. Obviously, we had hundreds of deployments, specifically within the dev environments over the past month, and it was only a few bucks here and there.
Yeah, I mean, you think about a build server, you want it to be up and active and ready to take jobs so you can deploy anytime. So traditionally, if you were running just Jenkins, you would have this massive machine running all the time. You could turn it off at night, but it's expensive. With this, you only pay for the compute during the build job. And if you get 100 jobs being built at one time, it can run it all in parallel, so it's much quicker. So it's cheap.
Yeah, and one more thing to add on to the build component is you can actually reduce the time of your builds on AWS Code Build if you pre-create some of those Docker images. So if you're using a vanilla image, you would have to download Maven, it would have to download the dependencies, which takes up a few minutes. You could potentially pre-create an image, specify that as the image you want to use for AWS Code Build, and you would reduce your time even further, reducing your cost even further.
And there's also, we launched a service last year called CodeStar. And CodeStar lets you basically deploy, you pick the type of application you want, whether it's Lambda, whether it's a PHP app, you pick, and then where you want to run it. Do you want to run it on EC2? Do you want to run it on Lambda? And it'll set up this entire pipeline for you in a matter of minutes, so it's really slick. So if you want a quick start, CodeStar is fantastic for that. Any other questions? Yes. So, are you leveraging, good question, not yes to that.
We are not leveraging Fargate at the moment. We did look at Fargate when we had these discussions last year, but at that point in time, Fargate was not HIPAA compliant, so it wasn't something we could consider. Is Fargate something that we're going to absolutely look at? Yeah. Q1, when we're looking at Kubernetes, we will also look at Fargate. In fact, for some of the other areas, such as the dynamic dispatchers, we're already considering leveraging Fargate, but again, that's highly dependent on compliance and security. So as long as we do our due diligence and those are satisfied, we could potentially move on to that.
Right. So now it's eligible for it, and so it's a potential candidate. Yeah. There's some great stories of customers using Fargate. It's highly adopted. really simplifies managing these containers. You don't want to have to manage the infrastructure that has those containers, so great approach for it. Any other questions? All right, well, thank you very much. Round of applause.